Hey, everybody. So I'm going to do a little explanation here about, critical values, and really about how we use them. Um, they're one way to see them as a just another way to look at our hypothesis tests. All right, so they're related to the p-values, and but anyways, let me just go through it and explain what they are. So I've got a generic hypothesis test, situation test set up here. So I've got a null hypothesis that there's a mean of 10, and an alternative hypothesis that the mean is greater than this. And this is coming from a population whose standard deviation is known to be 1.5. And we want to test this claim, this alternative hypothesis, with an alpha of 0.01. Okay. And so let's see. Oh, right. And we have a sample mean taken of 10.35, right? So we have our, with a sample size of 100. So we've taken our sample and it's a little bit higher, and we want to test, is this enough, higher enough that we reject the null hypothesis? So our standard way of doing this, and this is a perfectly reasonable way to do this, is to first, let's identify the situation we're in. This is type 1, where we know the population standard deviation. And so we want to compute our test statistic, which in this case is a z-score, right? Which is going to be x bar minus the mean over the standard deviation divided by the square root of n. So in this case, that's 10.35 minus 10 over 1.5 divided by the square root of 100, or 10. If you work this out, 2.33. Okay, there's our test statistic. And then we can compute the p-value by saying, computing the probability. So our p-value is going to be equal to the probability of having a z-score greater than or equal to this, under the assumption of the null hypothesis, right? And we can go to a standard, a normal distribution calculator. So I've got one here. I want to compute having a z-score over 2.33. I get 0.0099. Okay, 0.0099. So that's my p-value, right? Notice that my p-value is less than alpha, right? 0.0099 is less than 0.01. It's just barely less than it, but it is less than it. And that means we reject the null hypothesis. In other words, we're saying this is rare enough. If the null hypothesis were true, we would expect to get a sample like the one we got less than 1% of the time. And that seems too strange to us, that it's more likely the null hypothesis is false or is not true. So we're rejecting it. And we don't know what the mean might actually be, but we think it's bigger than 10 because of the sample that we got. Okay, so that's the standard way we would do one of these hypothesis tests. Let's think about it another way, though. Let's think about what we let's draw a little picture here. Here is our standard normal distribution, right, with the mean of 0. What is that meaning of alpha, right? So alpha is kind of a limit on how rare something has to be. How do we measure how rare something is? Well, the probability, right? The lower the probability, the more rare we think it is, should happen, okay? So in this case, because we're measuring above the mean, more rare means further away, right? Because we're going to be measuring the probability of that value or higher, right? So the way we can think about alpha on this picture is alpha is going to be the area in one tail, in this case, the tail going above. So alpha is up here. Alpha is that area, right? What if we ask ourselves what z-score would give us this area above it? So we can go to an inverse normal distribution, put in 0.01 above, and we get 2.326. In other words, if you have a z-score of 2.326, the area above it is 0.01. Okay? This we can think of as a critical value. Why is it critical? Well, let's think about where our test is going. We're going to test the p-value and compare it to alpha. In other words, we're going to test the area above the z-score we get and see if it's bigger than the area given by alpha. Well, looking at this picture, if my z-score is below 2.326, let's say just drawing it in over here, the area above that value is going to be the red area plus the blue area. It's going to be larger than 0.01, right? I don't know what it would be given some z value. I don't have to know, but I know it's going to be bigger. Or on the other hand, like in this case, we got a number 2.33, which is just barely above that critical value, but it is above. That means it's the area above this has to be less than 0.01. Remember, 0.01 is the area above this, well, now green line. Let's go back to black. Above this black line, shaded in red, that's area is 0.01. The area in green, the one above our z value, is less than that because it's missing some of it, right? And so if we wanted to, instead of comparing the p-value, we could simply compare our test statistic. In this case, note that 2.33 is greater than 2.326, and we'll make the same conclusion that we're going to reject, because in this case, we have to look at the picture, right? It's not always going to be above or above. If we were doing a different hypothesis test where we suspected the mean was lower, then we'd have to look at this in the other direction. So to use this critical value, we need to understand the picture well, right? Sometimes people will call the numbers above the critical value the rejection zone, right? So if you get any z-score or test statistic above that, then you would reject it. You don't ever have to find out the p-value in this case if you do it this way, as long as you understand this picture and which side of the line you will fall on to reject or fail to reject, right? Maybe another way to say it is above any outcome over this critical value is more rare than we're willing to accept that the null hypothesis is true. Versus on the other side of it, it's rare probably, but not rare enough for us to draw a conclusion, a strong enough conclusion to reject the null hypothesis. Okay, so that's the idea of a critical value, this cutoff point on one side where your p-value would be smaller, on the other side your p-value is larger, which determines the outcome of the test. So it's just really the same idea. We're still using the critical value to see is the area bigger or smaller, which is just another way of saying is the p-value above or below alpha. Okay. All right, let's look at this in one other way. Let's take a very similar situation. Let's take almost the same situation. We'll take H0 is that the mean is 10. We'll still be coming from a population with a standard deviation of 1.5. But let's say our alternative hypothesis is that it's just not equal to 10. Maybe we don't trust the agency that came to this conclusion. We're suspicious of their methods, so we just think they're wrong. We don't have a sense necessarily in what direction And we're still looking to test with an alpha of 0.01. Well, suppose we still went out and got that same point sample. Okay. So now let's, instead of computing the p-value, let's do this by looking at these critical scores. So here's our picture this time. Again, trying to draw standard normal curve. Right. Well, we have a two-tailed test now, because now we're saying it's not equal to 10, but we don't know what direction, so we have to look both directions. So pretend this graph that I've sketched is symmetric. What we're looking for, so if alpha is 0.01, the confidence level then is the rest of it. There's going to be 0.99 between, just like up here. I didn't write this in, but we had 0.01 above, which means there's 0.99 below. Now we're doing between. Well, what does that mean? On the outsides, that means the area in this upper tail is 0.005 and the same in the lower tail, right? So it's that 0.01 area, but split in two. Okay. So let's take a look at an inverse normal distribution calculator. And we will, let's see, we want to know what z-score has 0.005 above. Oh, I'm not in the inverse thing. That's why I'm putting things in the wrong spot. Pardon me. 0.005 area above. And we get a z-score of 2.576. This, by the symmetry of the standard normal distribution, we'd have a negative 2.576 below. So now we have two critical values, a positive critical value and a negative critical value, right? So when we have this two-tailed test, we have these two critical values. Let's think about this zone of rejection or rejection zone idea. We reject the null hypothesis when our event is so unlikely that it pushes us beyond the bounds set by alpha. In this case, this is going to be z-scores outside of these two. So I'll just call this the rejection zone. And in the middle, any z-scores at or between those two, we would fail. We'll call it the fail to rejection zone or something like that. Okay? So that's the idea. We don't, in this case, we won't actually know whether or not, we don't have to compute the actual probability. We just need to know where it lands relative to these numbers. So, excuse me, we would compute our z-score again, but of course, it's the same z-score that we got up above. However, but because we're doing a two-tailed test, we've split that area in half. Our restriction's a little tighter. So now 2.33 falls about right here. And so in this case, we would fail to reject. Okay? In this case, we would fail to reject. Okay? So that's the idea. That is our how we can use the critical values. The advantage of them is when we do things, especially with the standard normal distribution, where you have alphas of like 0.01, 0.02, 0.05, and you see the same ones over and over again, those critical values are always going to be the same, right? Anytime you do a one-tailed test with an alpha of 0.01, as long as you're using the normal distribution, right? When we use the t-scores, it won't apply. But this will always be the critical value. And so then you can simply compute your z-score and compare it to that, right? Okay, that's it for this one. That's all I wanted to say about critical values. Thanks, everybody. I will see you next time.